Hello folks, today we are going to start talking about solutions. When we talk about a solution, what we're really talking about is a homogeneous mixture. So we have more than one pure substance evenly distributed in similar particle sizes mixed together. So when we think of a solution, we typically think of the state of the solution as a liquid, but we can have all three states of matter represented in a solution. And a solution is going to take the phase of the solvent. So air, just the air that we breathe, is a homogeneous mixture of nitrogen and oxygen and carbon dioxide and other gases. And so just the air that we breathe is technically a solution. Alcohol dissolved in water is an example of a liquid being dissolved in a liquid, giving us overall a liquid solution. Brass is an alloy of different types of metals, a solid dissolved in another solid. And then we can think of carbonated water and sugar solution as being a gas and a solid dissolved in a liquid. And those kind of feel like what we think of when we say solution. It's where we'll spend most of our time today. And we can even have things like a gas dissolved in a solid as well. So the main solvent that we are going to deal with today is water. Water is our universal solvent, and it can dissolve many different types of substances. Remember, water is polar. It has an uneven distribution of electrons. And because oxygen is so electronegative, oxygen gets that slightly negative charge. Because it's a polar molecule, it can dissolve other polar things. And we use the phrase like dissolves like when discussing solubility, that polar substances will dissolve other polar substances. Non-polar substances will dissolve non-polar substances. Like dissolves like. And just some common terminology, make sure we're all on the same page. The solute is the substance being dissolved. The solvent is going to be liquid water in most cases, but our solvent will be the substance doing the dissolving. And an electrolyte, remember, is when we have an ionic compound dissolved in water, and that solution can conduct electricity. So we're getting a dissociation of ionic compounds into cations and anions. That charge can then carry electricity. Our strong electrolytes conduct a current very efficiently. So those are going to be our soluble salts, strong acids and bases, and they completely ionize in water. Our weak electrolytes will only conduct a small current. We'll have a dim bulb that glows, and some ionization, but not complete. And then we have our non-electrolytes where no current flows, it dissolves, but does not produce any ions. So for example, sugar in water, sugar is a non-electrolyte. So when we're talking about solutions, we need to talk about how much solute is in the solution. And so we use something called molarity. We represent molarity with a capital M. And so molarity is just moles of solute per volume of solution. So if we're dealing with a liquid solute, that liquid has its own volume. Our solids have their own volume. So we're looking at the total liter of solution at the end to give us our molarity. So if we have, for example, 3 molar hydrochloric acid, that would be 6 moles of hydrochloric acid for 2 liters of solution. If we were to reduce that, 3 moles per 1 liter. And we want to make sure that our denominator is in liters. Milliliters is a common measurement we also see, just because a lot of times that's what we're using in a science class is a smaller scale using milliliters instead of liters. So just move your decimal places as needed. So let's do some practice. A 500-gram sample of potassium phosphate is dissolved in enough water to make 1.5 liters of solution. What is the molarity of the solution? So this problem has a little bit of a mismatch in that we are given grams, but we are asked for molarity. So we're going to have to do a molar conversion using our periodic table and molar mass in order to get to moles, and then we can plug that into our molarity equation. So I have given you the molar mass of potassium phosphate, 212.3 grams per mole. So 212.3 grams per mole is our conversion factor. We've been given 500 grams. So 500 grams divided by 212.3, just so we can see our molar conversion. So grams on the bottom to cancel, 1 mole on top. That's our mole map in action. And we get 2.355 moles. Then we just divide by the volume of the solution, 2.355 divided by 1.5, and our molarity is 1.57. With these problems, we just see that I cannot measure a mole directly. It is a function of the element and the compound's composition and its molar mass. So I need to know the molar mass of a compound in order to figure out how much solute I need to add to get my desired solution. And another example of molarity, you have a 10 molar sugar solution. What volume of the solution do you need to have 2 moles of sugar? So our equation, big M equals moles per liter. Plug in what you know and solve for the unknown. 10 molar equals 2.0 moles over X. Multiply by X on both sides to get rid of our denominator. 10X equals 2. Divide both sides by 10 to get X by itself. And so you would have 0.2 liters of solution. So 200 milliliters when all is said and done. So with a molarity problem, just remember that molarity is moles per liter. If you've been given grams, convert, and then just make sure that you're using the proper unit for volume and solve for your unknown. So in Chem Lab, when I'm making solutions and setting up a lab, that first example we did with our solid and the grams, that's what I do a lot of the time. I go to the stock room, I grab the salt, and I weigh it and dilute it, add water. But there's a lot of things that are back in the stockroom that are concentrated or a stocked solution. So we buy a big jug of hydrochloric acid and we use that all year, and we dilute it to make it safe for people to interact with. Concentrated hydrochloric acid will cause chemical burns. So I have to dilute it to make sure that it's concentrated enough to work in lab, but dilute enough to be safe for everyone to use. So when we're doing a dilution, we add water, and so that changes the concentration, but it does not impact the amount of solute. So M1V1, we have our moles per liter times liter, and then we have our M2V2, which will be still moles and per liter times liter. So those liters will cancel, and the moles will be the same. So what we're really trying to make sure is that the moles are equivalent before and after dilution. So our formula for this is M1V1 equals M2V2. Inverse relationship, the more concentrated molarity will have the smaller volume. And so as we add volume, the molarity will decrease. Just think of a common example. A lot of people buy those little flavor bottles, that little brand of, fruit punch or lemonade, and you squeeze the bottle into water. That flavoring gets dissolved in the bigger glass of water, and now you have flavored water, but the little bottle sold to you is concentrated, and then your final solution is more dilute. But the number of flavor molecules in those original drops is the same as the number of flavor molecules in the whole glass. So if we have a 0.5 molar solution of sodium chloride in an open beaker, and it sits on a lab bench, which of the following would decrease the concentration of the salt solution? So if you look over these options, give you a second there. So adding water to the solution would decrease it, make it more dilute. Pouring some of the solution down the drain would have no impact on the concentration because everything's evenly dispersed. It would impact the volume of solution, so that would be unchanged. Add more sodium chloride to the solution, well, that would increase the concentration. And letting the solution sit out in the open air for a couple of days. So in this case, the volume would go down, but the moles would stay the same of solute, so concentration would go up. So our answer, when all is said and done, is A. And just to practice with this calculation, what is the minimum volume of a 2.0 molar NaOH solution needed to make 150 milliliters of a 0.8 molar NaOH solution? So our formula, M1V1 equals M2V2. I try to make the original M1V1 the stock solution, the more concentrated one. It really doesn't matter. What does matter is keeping the molarities and the volumes matched together. So I want to make 150 mils of a 0.8 molar solution. So that needs to be my second molarity and my second volume. They have to go together. So with a problem like this, I find it helpful to write out all my variables. My molarity, my original molarity is 2.0. I don't know the original volume, but I know M2 and V2. So we just plug everything in. 2.0x equals 150 times 0.8. And then we can simplify and solve for x. 2x equals 120. Divide both sides by 2, and we get 60 milliliters as our answer. Molarity is moles per liter. If you wanted to convert everything to liters, you could, but just know that if you were converting to liters and then back to milliliters, that conversion factor would cancel out. So you don't actually need to convert. It's just if your original volume is milliliters, your final volume will also be milliliters. All right, and here is another problem for us. 10.0 milliliters of a 0.3 molar sodium phosphate solution reacts with an excess of lead 2 nitrate solution. What precipitate will form? So we're going to use this information in the second part of our problem, but let's think back to some of our earlier days. I want to know my precipitate. So I have sodium phosphate, so that is my Na3PO4. So phosphate PO4 3 minus. And we are going to add to it excess lead 2 nitrate. So Pb nitrate is NO3 with a charge of -1. So NO3 2. And now we're going to have a double replacement. So remember, our cations are going to switch places. So we are going to have NaNO3, sodium nitrate, sodium cation +1, nitrate -1, and lead 2 phosphate. Remember, charges will not change on a transition metal in double replacement. So swap and drop our charge, Pb, 3 from the phosphate, PO4, 2. And which of these is my precipitate? Remember our solubility rules. Sodium and nitrate are both always soluble in an aqueous solution. So those are going to remain aqueous. And let me change my pen color here. So this will be my solid, my lead 2 phosphate. And then we're going to need a balanced solution for the next part of our problem. So let's take a look in balance. I see with my sodium, if I start with just my sodium 3 and 3, that's going to give me an odd number of nitrates. So I'm just going to go ahead and actually let's start with our lead here because that's going to give me less problems. So 3 lead nitrates will give me 6 nitrates altogether. So I will need a 6 in front of my NaNO3. 6 sodiums, only 3, make that a 2, and that is a 1. Okay, so now I have a balanced equation. I know that lead 2 phosphate is my precipitate. So there is my balanced equation all typed up nice and neat on top. What mass of precipitate will form? So we're going to do a little bit of stoichiometry in here. And since I see mass, I know I'm going to need molar mass of lead 2 phosphate at some point. So I've put that for you, 811.5 grams per mole. So the steps for solving this equation, I need to get to my moles of sodium phosphate and then get to my lead 2 phosphate. So the original problem told us that the molarity was 0.3 moles and that there was 10 milliliters of it. So molarity is moles per liter. I needed to turn that into liters. So move that decimal place over 3. So 0.3 equals x divided by 0.01, multiply both sides by 0.01, and we have 0.003 moles of sodium phosphate in the solution. Now that we know moles of sodium phosphate, we can use the molar ratio, and then we can go ahead and plug in our molar mass to get to our final problem. So if you want to go ahead and solve that on your own, give that a little try. But we want to set up our moles of sodium phosphate, so given from the problem. Then we're going to use our molar ratio. Moles of sodium phosphate will cancel. We are now in moles of lead 2 nitrate, and we can use our molar mass. So 0.003 times 1 times 811.5, all divided by 2, gives us 1.2 grams of lead 2 phosphate.